Okay, folks, so next talk is Pierre Meyer, who will tell us everything you wanted to know, but were afraid to ask about topology-hiding computation.
Thanks, Ivan, for the introduction. So before I start, don't worry, I'm not assuming any familiarity with THC, topology-hiding computation. I'm just assuming you know what MPC is, which I think is fair at this point in TPMPC. So the goal of this talk is perhaps to introduce you to the beautiful theory of topology-hiding computation. And I'll do that by presenting a line of work with all of these wonderful people. So Marshall Paul, Ellen Boyle, Ran Cohen, Lisa Cole, Tal Malkin, Tal Morand, and Alexander Binstock in the last one. So our goal here was to try and understand what were the minimal assumptions required for topology-hiding computation. Now, I think I've said topology-hiding computation enough that I need to define it. So I'm actually thankful that last night we had a couple of talks about MPC over incomplete networks, because that way I feel justified in saying that the usual setting of assuming that every party can talk to every other is very unrealistic, especially as the number of parties grows, and that in practice, although this is very much a theoretical talk, in practice, we usually have to assume that only some parties can talk to some others. And in fact, I'll be talking about a setting which is perhaps even more realistic, where each party only knows who they are talking to. There's no good reason to assume why they should know who everyone else is talking to. So we could call this the unknown network model. And what is topology-hiding computation? It's basically, assume you are trying to achieve MPC in an incomplete network. Initially, each party only knows their local view, and the extra security requirement from THC is that the parties should learn nothing more about the graph than what they already know. So first of all, what could it possibly mean to learn information about the graph? So let's look at perhaps the most trivial task, which is semi-honest broadcast. Now, in the setting most of you are accustomed to, semi-honest broadcast is not much. I wouldn't be giving a talk about semi-honest broadcast. Send messages along, and since people are following the protocol, they will be passing on the information. And in fact, this is called flooding broadcast. The broadcaster sends the message to their neighbors who pass it on and pass it on. Now, if you do that, the round in which you receive the message leaks something about the topology, more precisely about the position of the broadcaster in the network. And so you can remember these two things, if you will, like this revealing your own distance to the broadcaster and your neighbors, because this is going to show up a bit later. Okay, so now that we know what it means to reveal something about the topology, what does it mean to reveal nothing? And in short, we have a simulation-based definition, which means that, let's say you corrupt the view of a party, you should be able to simulate the view of their protocol, their view, given their local view on top of everything you would expect. You don't necessarily need to remember that, just if you were wondering how we could model such things. So more precisely, and don't worry, we won't be using this barbaric notation, but a topology-hiding protocol, it's a graph class, a functionality, and an adversary. So I'm mostly going to talk about the graph class because that's the important part. It means that everyone participating in the protocol knows beforehand that the graph belongs to a certain class. For instance, you know it's connected, you know it's highly free connected, you know it's a cycle, that sort of thing. And you should not be, you know this information at the start, and you should not learn anything more about which specific topology it is. And mostly we'll be talking about topology-hiding broadcast and topology-hiding general computation, THP and THC. And if anyone knows what THA is, I'm interested because it's a bit confusing. Good. So hopefully we're now all on the same page as to what topology-hiding computation is. Now, can we even achieve this notion? The answer is yes. We have a bunch of different feasibility results. In particular, I want to bring your attention to these 2 points. If you have oblivious transfer, or like some with a few caveats, we know how to do semi-honest topology-hiding computation, tolerating all but one corruptions, on the class of log diameter graphs. So that's a bit of a restriction we'd like to get rid of. And if you are willing to replace your OT assumption with DDH, LWE, QR, and very well-founded, I'm sure, you can achieve THC on the class of all graphs. So what we'll see today is that we're kind of bridging the gap by using this flavor of OT assumption in order to build topology-hiding computation on all graphs. Now, because I talked about the feasibility results, I have to say a couple of words that before this line of work investigating the minimal assumptions of THC, we did know a few things about some requirements of it. But specifically, this is the line of work I'm talking about. So the first one I'm not involved in, but it really raised this question. So I thought it was only fair to mention it in this talk. Now, what our results show? So the question is, what are the minimal assumptions for topology-hiding computation? Our results suggest that there are 2 regimes. The first is what you could have called high-end THC. The task is to achieve general computation. You have to be able to achieve every single functionality, like say secure function evaluation. And the second world, low-end THC, is where we have a specific task in mind. And what our results suggest, it's still a question at this point, but our results suggest that there are 2 very different answers to these 2 questions. In the first setting, we could, let's say that all of the data points we have point to the assumptions required for MPC on incomplete networks to be the same as for topology-hiding computation on those same networks. So what I mean specifically by that is that, so you should read this from right to left. So these are the assumptions for MPC on incomplete networks. Do you have an honest majority? If you don't, you need OT. And if not, you have to ask yourself, do you have a sufficiently connected graph? And then it's either key agreement or you can just do it information theoretically, which I use as a catch-all for statistical, perfect, whatever you'd like. Now, we'll see, and we'll expand on a second on why we think that the answer still holds for THC. But before I do that, I'll mention we have a couple of results in the topology-hiding specialized computation setting. And what those, they are very sparse data points, but they show that there are some black box separations between MPC and THC. So at this point, I couldn't even venture a guess as to why that is, like what is the relation between functionalities and graphs, which makes them so different, but we know that they are different. And so I have a final slide with pointers to the papers. So if you're interested in the second part and you want to know what phantom bridge or an artificial overextension, which are the proof techniques involved in like showing these separations, I invite you to have a look at the TCC 20 paper. Good. But for this talk, let's focus on the high-end notion of THC, general computation. Excellent. So, in a bit more detail, what have we shown so far? So, for one corruption, which we have to start somewhere, we proved this conjecture like for the first 2 settings, like the honest majority setting. Now already, so in MPC, one corruption is a lot easier than it is for topology-hiding computation. And well, as evidenced by the black box separations I mentioned earlier. But the purpose of this talk is mostly talk about the final line, which is the latest result. So assuming we have an oblivious transfer protocol which uses constant round and has a constant overhead in communication complexity, which are assumptions we'd like to get rid of eventually, but it's still a significant step, I hope. We show that we can achieve topology-hiding computation on the class of all graphs. Now, if anyone cares about such things, we actually make a non-black box use of the OT protocol, and it's important that it be an OT protocol. But again, we'll see it when we get to it. Good. Now, sorry, yes. Now the focus of this talk will now be to explain how we get to that point. Like, how do we build topology-hiding computation on all graphs from this notion of oblivious transfer? So, for those familiar a bit with the previous THC literature, they are on a high level. We're combining two ideas from two previous papers, and kind of building something really new from the intersection of the two. So for people who aren't familiar with these networks, I'll give a very high-level description of maybe some of the ideas. So let's start with ALM 17. Oh, on the other side. This idea of using correlated random walks in order to explore the graph. So what do I mean by that? Let's say you are trying to achieve topology-hiding broadcasts. That means that there is in your network someone who holds an input bit or a string, whatever, something they want to share with everyone. But as we saw with like the problem with the flooding protocol, you can't just pass it along in the plane, in the clear. You really have to make sure this broadcast bit gets to every point in the graph in a way that people don't know when it arrives. So you could think about achieving this. Let's for now assume that we have some kind of secure hardware. We just have a box where some form of an obfuscated box. You just have you have a hardware box, and whenever a party gets hold of it, they are allowed to put their input in there, and then pass it along. And what the box does at the end, after a certain number of steps, it releases some function of what was in the box. So for instance, in the case of broadcast, only the broadcaster would be putting the input in there, and no one else would be doing it. Now, one way to make sure it would get through the room would be I could set up this box and give it to Daniel, who'd pass it on at random through the crowd. Now, the issue with that approach is that if two parties are colluding, they can say, wait a minute, I got the box at step 2, you got the box at step 10. That means that there's a distance at most 8 between us. That's learning something about the graph. So the intuition on how they got around this problem was to say, every single party in the room is going to start with as many boxes as they need. And all of these boxes are going to be completely indistinguishable. And they're going to send one to each of their neighbors. Each person they're talking to is getting a box. Now, when you get some boxes, you get one from each person you're talking to, you shuffle them and you send them out. And if you follow each box individually, it actually follows a random walk. So we're going to have a few slides of explanation about this. But so globally, the way the boxes spread are highly correlated, but individually they're random walks. And what's nice about that is that we know from a very serious analysis that random walks cover crowds very well. Now, this is, if you will, the randomized graph exploration paradigm. And the randomized part makes it very topology hiding, like THC friendly. Now, the more brute force version, which I call like non-deterministic graph exploration, is the recursive approach. Let's say I, as a party, I have OT. I can do MPC. I do MPC with my neighbors. And now we've defined, if you will, an ideal party from this, which is the neighborhood party. Now, if everyone does that, and my neighborhood party talks to my neighbor's neighborhood party, we can sort of like recursively build on that and build like larger and larger neighborhoods. And so if you will, the message, the broadcast bit can go to being shared in the neighborhood, to the 2 neighborhood, to the 3 neighborhood, and so on and so on and so on. And this was the approach in the original topology-hiding paper. Now, they achieved it from oblivious transfer because, as I said, it's mostly recursive MPC. The main issue of that is that the recursion is too expensive. And one key insight we have here is how to make very efficient recursions by using random walks. But intuitively, the problem why the recursion is too expensive is that when you go from a k neighborhood in a graph to a k+1 neighborhood, you're only guaranteed to get one more party. Think of a path. The k neighborhoods don't grow that much. What we'll show here is how we can like really double the number of parties which gets the bit at each step of a recursion. So I think I've said enough high-level explanations, and we can go into back to hopefully beautiful drawings. So let's say you have parties which are in a directed path. Parties 2, 3, 6, and 7 are corrupt, semi-honest, and they're all colluding. So this is, by the way, this is no longer about THC for this one. This is a fixed graph. Everyone knows what it is. There's no unknown network. It's an MPC primitive which we'll be using to build topology-hiding computation. So let's say parties are in this configuration. So I'd like to introduce what we call locally simulatable MPC. And perhaps you guessed that what locally simulatable means is that if you have 2 connected components of adversaries. The idea is to say locally simulatable MPC is a stronger requirement than MPC that asks that you should be able to craft the views independently for different components. So it actually makes sense for for randomized functionalities. But it's simpler to think about it for deterministic ones, because you don't really have to think about like how outputs are correlated too much. And now the main reason of why this is interesting for us, why this notion of locally simulatable MPC is cool, is that if you run the same instance, you have a protocol, locally simulatable, and you run it twice with the same inputs. So you'll get the same outputs if it's a deterministic functionality. But you're allowed to use different randomnesses. Because it was locally simulatable, instead of matching the views like this, I could actually like just twist them around, right? If I give you a green view 1 and a blue view 2, you can't tell that apart from green view 1 and green view 2. So that's kind of this cool property we'll see as very useful in a moment. But I would like just to pause a second here and really remind you that this at this point is not about topology hiding. So hopefully, if this notion is of any interest, please let us know. But now let's demonstrate how it can be of interest for us for topology hiding computation. Sorry, before showing how it's interesting, maybe I should mention that we can in fact build this notion, otherwise it's a bit less useful. And the idea is to use, we like trees, we're in computer science. So we build recursive 2-party computation in a tree-like fashion. And the idea of why this protocol will in fact be locally simulatable is that if you look at a connected component of adversaries, so there'll come a time, if you look high enough in the tree, where they'll be completely engulfed in some 2PC, and so they will learn nothing. Now, the interesting part is that there's an interesting regime in the middle where they corrupt, let's say, an entire 2PC, like an entire one of those pink boxes, and a couple of adjacent nodes. And so what we show is that this structure is perfectly suited to achieve local simulation, and it's in fact like quite tight. We can't like push things as far as we'd like. So I truly believe there's something very interesting about this notion. So when the paper is out, eventually I'll invite you to all have a look. Okay, so we now have this. I'll just go back to this one. So assume now that for any, let's say we have a directed path. Thank you. We have a directed path, and we have locally simulatable MPC. How does that give us topology-hiding computation? So now we have to go back to this random walk idea. This like passing along hardware boxes which do the computation on the fly, if you will. So think about it this way. You're in a network. You are you, oddly enough, and you see 5 parties. Now you sample a random permutation. That's pi1. You sample a second permutation, pi2. And I'm going to stop here because I should actually go for whatever the number of nodes is cubed, but I'll stop here and just go from the local view to the global view. So this, well, it's not quite the same one, but you this time decided to sample another first permutation. Let's just follow one of those threads. Right, and with the analogy from before, it's like the idea of passing along boxes along each of the red arrows. Now, if the party, let's just focus on this branch of the permutation, if you will, and look at how it composes with the second permutation of the second party, and then you can go on like this, and eventually it builds a walk. And in fact, there should be a fourth path here. The idea is that like for every single vertex u in the graph, there are like these random walks spanning it. So now the idea is going to say, and notice that each party sampled their local view of the random walks, right? Each party sampled a bunch of permutations. So each party knows, let's say I sampled in round 3, I sampled a permutation. That means I know that I am the third party on a certain path. So I don't see the whole path, so I don't know the entire thing, but I know I'm the third party on the path, and I know that my predecessor is here and my successor is here, because I in fact chose the permutation. So this is why they are correlated random walks. Now, why is this highly compatible with the notion of locally simulatable MPC? So let's just look, for simplicity's sake, at just one walk. One walk through the graph is random, so it could go through corrupted parties many times. It could go through the same one several times, and it could go through multiple corrupted parties. And for our protocol, at the end of the day, to be topology hiding, we really want it that the parties do not recognize the walks. It's like the idea of these hardware boxes, you can't identify them. Otherwise, the entire thing breaks because oh, I was visited by this walk, you were visited by the same walk a bit later, we know we're not too far apart. And why this works is that if you run this locally simulatable MPC on this path, oops, I skipped ahead too much. Because it's locally simulatable, you can in fact like simulate the views independently and one by one. And if you remember what I said about, even if you had 2 different instances with the same inputs, and you could like kind of mix and match, this is exactly what's going on here. Let's say you're visited by 2 random walks. Well, in fact, you can't tell if they were from the same walk, if they were from different ones, because it exactly reduces to the above problem. Okay, so hopefully I've given you some ideas on how maybe like we can design like very interesting very strong forms of MPC from the same assumptions as MPC. So it uses the same assumptions as MPC, but satisfies a stronger requirement. So it involves new techniques, and it allows us to build topology-hiding computation. So just as a reminder, this is where we are right now. If you'd like to help us complete this picture, go beyond T=1, get rid of constant rounds, constant overhead, please let me know. Now I'll just finish this talk because I saw at the RUMP session yesterday that we had a contractor from NIST. So because we're talking about the foundations of topology-hiding computation, I'd just like to point out that we in fact showed that, like, if you had topology-hiding broadcast on this class of graphs, like if you just have a triangle or a path, it in fact is equivalent to key increment. So we have an implementation for that if you would like to update the recommendations. With that, I'd like to thank you all for your attention, and yes, point out that one of those two papers is on reprint right now.